bienvenidos al show Turfurk. El video de hoy es cómo se hace un símil logaritmo gráfico utilizando los datos quitados de la descomposición de una columna de agua. Ay, caramba, tengo algo en la garganta. Momento, necesito agua.
Vocal check. Let me try that again. And welcome back to Turdferg Show. Hey, alright, my voice working properly now. I have no idea what was going on before. But anyway, today's video is on how to do a semi-log graph. And in order to do that, we're actually going to be looking at the decay of a water column. I don't have a picture of a water column handy, but it's a very common lab. We use the same columns in physics that we use to do sound with for determining speed of sound. So we'll fill the column up with water, and then we'll open up a small valve or something at the bottom, and we'll let the water drip out. And if you've ever done this, heck, I challenge you right now, wherever you're at, grab the closest cup near you. And I want you, well, assuming it's styrofoam or something, poke a hole in that cup. And you'll notice when you do that the water runs out very fast at first, but then gets more of a trickle and a trickle and a trickle as the water comes out of the cup. And so in this lab, somebody every 30 seconds has written down the height of that column. So at 0 seconds, it was at 200 centimeters and so forth. This lab, and it's giving us some requirements over here, and it's saying that it wants us to do a graph of h height in meters versus time is what it's wanting us to make a graph of. Now, something interesting, when you look at this data, it doesn't behave right. Now, if you were in an Apex program or something, that's Alabama Physics Excellence, they might want you to go ahead and do a graph on this number. So I went ahead and done this. I went ahead and made a linear graph based on that data. Now, let's blow this out where we can take a little bit of a better look at here. Zoom me to the entire page. Look at this graph. So this is linear graph paper. And I want you to look at this data. At 0, it was 200. I couldn't get that on here. But at 30 seconds, 160 at 60 seconds, and it's continued to decline. Look at this. You should be able to quickly tell this is not a linear graph. And you might be going, what do you mean by linear graph, Turdferg? I mean this. There's no way for you to take a ruler, lay it on here, and then you be able to draw a best fit straight. Well, that's not even a straight line. But there's no way for you to draw a line through that data. Matter of fact, if you really look at that data, how do I get rid of this ruler now? If you really look at this data, what you'll actually observe is this. The data is actually making this curve. And that's great. And I drew a pretty halfway decent curve here. But the problem is this. I cannot take a slope from this graph. So I'm kind of in a pickle here. So how do I graph data that is logarithmic, being the key word here in nature? Well, it's easy. If you want to do a graph that uses log, then you need a piece of logarithmic graph paper. So what does that look like? Well, I've actually got a few samples here. This is a piece of 1 cycle log paper, and you'll notice it's very distinctive. Look at this. It starts with number 1 to number 2, and it works its way to 10 up here. And if you look, it starts out this huge bottom, then gets smaller and smaller and smaller as you go. And then this is what's known as 1 cycle log paper. This is known as 2 cycle log paper because if you actually take a look, it goes through this pattern, and then it repeats again. That's 2 cycle. This is 3 cycle log paper, and then this is called semi-log paper. And the reason why all these have been semi-log paper is because if you notice, the log scale is going up, but it's a linear scale from left to right. So whenever you see that, that's what you call semi-log paper. And that's what this graph will be on, or this video will actually be on today. There's actually something called log paper. This is a piece of 2 cycle log paper. And literally, that's how you could say this, log. I will do my next video on this. But if you look at this, you've got a log scale going up, and you've got the log scale on the x-axis. Let's go ahead and get right into how to do a semi-log graph. I've got a piece of graph paper already ready to go. Now, my data technically, based on my data, I should actually be using a 3-cycle paper. But let me explain something. How does this log scale work? Well, it's easy. Here, let me go ahead and let's find a piece of that 2-cycle. You see, what happens is this. On log paper, uh, what we do, and I'm going to see if I can't blow in. View, zoom in. Let's go in 75% maybe. I want to see it bigger. Zoom, show me more. And that's not nearly enough. View, zoom, I'm sorry. 150% there. Let's look at this piece of paper. This is what happens. First off, you're going to notice there's no 0 on the log paper. It starts me at 1. That's because a logarithm technically doesn't ever reach 0. So on this paper, let's say you want to graph this and say you want to make that 1. Cool, 1.0. 2.0, 3.0, 4.0, 5.0, 6.0. Right now you should be looking and being like, all right, well, Mr. Cole, we got this. This is easy enough. 7.0, 8.0, 9.0. And so that's 10. Cool. Well, here's the mistake. Most people then would want to naturally make that 11. But if you notice, it's already numbered for you. You jump scales. This is a log scale. If that is 10, 11 is actually that would be 11. This next line up, there's 20 lines here, so that makes every other one a 1. So that would be 11, 12, which means that actually this is the number 20. And so that's how this works. 20, 30, 40, 50, 60, 70, 80, 90, 100. Now, what if this was 3-cycle paper? Then the next scale would go 1,000. Every time you jump scales, you gain a 0 on your scale. So let's go to our graph today. And I'm going to be using a piece of 2-cycle log paper for my graph. Let's see if I can't find it and start doing it. Now, just like with any graph, I'm going to go ahead and do something. I'm going to go ahead and put my name and my date in the top right hand corner. I'm also going to put a title up here, water column decay. Every graph should have a title. And then you should have under that title, you should always say what it's going to be a graph of. And for me, this is going to be a graph of height in meters, because that's what my instructions wanted, versus time in seconds. So this little thing I'm doing, it's a way of telling my y and my x axis up here. So I'm telling someone what's a graph of, and I need that if I'm doing a lab with multiple graphs. So let's go ahead. I'm going to go ahead and do something. I'm going to go ahead over here, and I'm going to write h in meters. And I'm going to go down to the bottom, and I'm going to do this. Now, you're going to notice something that's different from most videos I do on graphing. Usually when I start talking about graphing, one of the first things I do is I draw an axis on here. Now this is going to blow your mind. Most of the time, if you watch one of my videos, I will step in like 1 block left and 1 block up and make my axes. You don't do that with a log graph. A log graph will be the only time you actually hear me say this. So I hope you're ready. It's going to be amazing. I'm excited. I hope that you are. Watch what I'm about to do. Look at where I'm drawing my axis. And my scan's a little crooked, so forgive me for that. Look at where my axes are actually being drawn. You actually, on a semi-log or log paper, the border of the graph will actually be your axis on there. So that's a little something that's different. Now I'm going to go back at my data. My data is going 0, 30, 60, 90 for time. So let's go through and let's see if we can't get our time down. I'm going to blow it back in a little bit again so that I can see a little bit better. So I've got my axes on here. Okay, so left to right is normal paper. That's why, again, this is called log, semi-log paper. So I'll go 30, 60, 90, 120, 150. Oh, where's that going? 150, 180. See if I can't complete all these lines across here. 210. Not the most exciting thing in the world. 270. 300. Whoop, 330. 360. 390. And finish at 420, which was my last data point. Now, going up, my numbers actually ran from 9.4 centimeters to 200 centimeters. But the graph actually wanted me, or the lab wants me to graph it in meters. So I'm going to have to make that, say, for example, 2 meters. Now, 9.4 centimeters. To really graph that, I would need 3 cycle paper. So I'm actually going to make my first data point 11.8 centimeters that I'm going to graph, which means my graph is actually going to be, in terms of meters, that's going to be 0.10, 0.20, 0.30, 0.40, 0.50, 60, 70, and hopefully you're catching on to how this works, because again, it wants it in meters, 80, 90, and then we get to here and it becomes 1. Now remember, this is what makes a log graph. When you hit 1, then that makes the next one 2. So that's actually 2.0. So that would make that next line, for example, 1.1. I just want to make sure we've got all this kind of addressed. So every other line would be 0.1 as we go up through here. And that's because there's 20 lines. So every one of these would be an 0.5 that we're looking at. So you have to be aware of how this scale changes. You've got 20 lines here, but then you've only got 10 lines here. So you've got to be looking at your scale as we do this graph. All right, I'm actually now to go ahead and start my graph. My first data point was actually, it said at 0 seconds, my column was 200 centimeters, which would be 2 meters on the nose. So at 0 seconds, I'm going to go ahead and put a dot right there. Now, my next data point was at 30 seconds, and at 30 seconds it said 160.3. Therefore, for me, I'm going to graph 1.60 meters, since that's what I want. So where would 1.6 be? So here's 30 seconds, this first bold line over. So we can do something here. 1.1, 1.2, every other line is a 0.1. 1.3, 1.4, 1.5, 1.6. So at 1.6, I'm going to put me a little blue mark for a data point. And now we should be kind of on a pretty good roll. My next is at 60 seconds. It says that I'm at 128.2. So let's do that. At 60 seconds, 128. So that'd be 1.28. So essentially I'm what? 1.3 here, right? So let's see if I can do this. So there's 1. And then let's go up from there. So 1, 1.1, 1.2, 1.3. So 1 point, I want it in blue, thank you very much. So my next point is going to be approximately right there. It's hard on these graphs because, well, I've got kind of a big pen since it's digital. And then take a look. Next is 90, it's 1.04. Well, that would actually be, that first line be 1.05. So we're going to be right in front of it. And then we're going to take a big jump. It's my next data point. Says at 120 seconds, I'm at 83.5 centimeters. So that'd be 0.835, and I'll make it like 0.84 just for our own ease, which means I'm on this line and I need to go up to where 0.85 or 84 would be. Well, there would be 8, and I'm right up in here. Bam. So there would be my 8.4. Now, I'm not going to keep doing this graph. I'm going to go ahead and do this. Here's a graph. I've already got all the data plotted. So let's go ahead. So what do we do now? All the data is plotted across. And if you can look, this is what's beautiful. Here's the linear graph we tried making. You can look at this curve, and we couldn't do a slope. But now look at this graph. By plotting it on the log paper, we've got this nice straight line. And what that actually means is this. I can now treat it like any other graph that we would ever work. As in, I can take a ruler, I can take that ruler, lay it on here, and I need to make again, what's called a best fit line. Hopefully you've heard me use that in other videos. That means I don't actually have to touch any of these